Okay. Can you see it? Can you
Yes,
see?
sir.
Okay. I'm correctly audible.
Yes, sir.
Okay. Fine. So let me introduce myself. I am Moinak Ghoshal. I'm a PhD student at Indian Institute of Science, Education and Research, Kolkata, IISER Kolkata, and I have been assigned as the TA for this course entitled as Fundamentals of Spectroscopy, which was instructed by Professor Sayan Bakchi and Professor Anirban Hajra. And this is the assignment related questions of for week 4, where I'm going to discuss some questions which will be beneficial for you to solve questions regarding these assignment that you will going to solve. Okay, so in the very beginning, I am going to give a brief introduction about the previous week's assignment, what I have discussed. So these concepts were discussed in the uh, previous class or previous live session. Okay, so first term was that angular motion. What is the relation between this linear motion and the angular motion, and also what is the relationship between this linear and angular? How to convert any quantity in the linear motion to some quantity in the angular motion, that was already discussed. And then there was a concept of inertia, and it was noted that like just like velocity in linear motion has something like angular velocity in angular velocity in angular motion, which will denoted by as omega. Just the same thing for mass in angular motion, there was something which is called moment of inertia. Okay, this is called moment of inertia. It is just the angular part for mass. And then there was calculation of energy for rotational energy levels. There was a calculation of energy which was given just in terms of nu bar. I can write it as nu bar, which can be defined as B into J into J plus 1. It was discussed that the nu bar, the energy of any rotational level, can be defined in this way. That is, nu bar is equals to Bj into J plus 1. Then the concept of rotational quantum numbers were introduced, which is here written as J. This was introduced, and then there was a discussion on what should be the condition for a molecule to show rotational activity. That is, all molecules will not show rotational activity. It was discussed that for rotational active or microwave active molecule, you have to be have the condition like your permanent dipole moment should be non-zero. You should be non-zero. Okay, so this was discussed, and for this it was also said that the homonuclear diatomic molecule like H2, N2, C2, this kind of molecule which is homonuclear diatomic, they don't have a permanent dipole moment. But HCl, BF3, these different kinds of molecule, heteronuclear diatomic molecules, they have a permanent dipole moment. So they show the microwave activity. And then concept and calculation was done on a reduced mass. What is a reduced mass? If it was said that for a two-body system, when which approximated as a rigid rotor, that means the bond is fixed between these two molecules and this is rotating. And then it was conceptualized that to consider these two bodies into a single body. And for this, to define this single body, another mass term is introduced, which is called reduced mass. And the expression for reduced mass was that this mu could be defined as this mu and this mu is completely different. Okay, this is for dipole moment and this is for reduced mass.
Yes,
So
sir.
mu could be defined as m1 m2 by m1
M1 plus M2.
exactly. Mu should be m1 m2 by m1 plus m2, where m1 and m2 are the masses of the two bodies. Then the selection rule for rotational spectroscopy was discussed, and here the concept of transition moment integral was introduced. We showed that this transition moment integral should be non-zero for any transition to happen. For be it rotational, be it vibrational, or be it electronic, anything. For any transition to happen, your transition moment integral should be non-zero. Just a minute. Afghanistan, Okay, then finding the energy gap between two successive lines in the rotational spectrum. In the rotational spectrum, it was shown that the rotational energy levels or rotational lines are separated by constant distance, which is defined as 2b. You have shown that in the previous lecture. And also, there was small peaks were appeared in with the normal peaks in the rotational spectrum. This was discussed also for the carbon monoxide case. It was shown that with the normal peak or with the genuine peak, there is some small peaks which are appearing just beside these peaks, which was discussed due to presence of isotope, and due to their natural abundance, their intensity was very much low. And then the concept of degeneracy and how to calculate this degeneracy, this was also discussed. This how what is degeneracy and how to calculate it. And also then the rotational quantum number mj, this was discussed also. This rotational quantum number also, this is mj, and how it is related to the degeneracy of a rotational level, it was also discussed. Okay, this was the previous week's assignment, and previous week I have solved some problems regarding these topics. So in this week I'm gonna do, like I have in this week, there is a lecture on degeneracy of the rotational level. What I have said in the earlier section, that here you can see this the degeneracy of the rotational level was there, and you know it was given by this term 2j plus 1. But it was shown that this rotational level degeneracy is lifted in presence of external perturbation. When there is no perturbation, no field is there, this rotational, all rotational lines are the equal energy. Okay, as you are pushing some electric field or some magnetic field, so then what happen? This rotational energy levels will change. Okay, they will not be degenerate. They will take the different. They will take the different energies. Just like if you know about Jan Taylor, you can see that in case of Jan Taylor, this degeneracy is broken. Okay, just like the same thing. In this case also, the degeneracy is lifted due to external perturbation. And also, the intensity of the rotational lines in the spectrum was also discussed. And it was discussed that the which on which factor this intensity depends. The first thing is transition probability. What is the probability of transition? If the probability of transition is more, the intensity will be much more. And also, another thing is very much important, that is the population of the initial state. What do you mean by that? That means from which state transition is happening. This is very much important. Suppose in your state you have 10 molecules which is going to the excited state, but in another case you have 100 molecules, you are getting it to the excited state. In the second case, you can see that since the population is much more, so it is intensity will be much more. Okay. Then in the next lecture, it was discussed about non-rigid rotor approximation. In the up to the previous lecture, it was already discussed about the rigid rotor approximation. That is, the bond length is fixed. Bond length is, bond length is not changing. Okay. But then another concept will be introduced, that if the bond is changing, suppose this is a rigid rotor, this bond length is not changing. This bond length is fixed. It is just rotating. Okay. But when suppose the bond is not fixed, in a molecule the bond is not fixed, it is actually getting vibrated. Okay, so with rotation there is also a vibration attached with it. So that's why not rigid rotor approximation becomes very much important. Okay, so then another equation was changed, and there was a concept of centrifugal distortion. That is, the atoms are moving outside, trying to get outside. And then the expression was this new bar, which was defined as b into j into j plus 1, and another term will be there due to non-rigid rotor approximation, which is known as d j into j plus 1. Here d is also known as, sorry, there square will be there. Yeah. So here d is known as centrifugal constant. Okay. So this concept was introduced, and from that, they are when you have calculated the energy difference between two levels, that is delta of nu bar, you have seen that another term was introduced, that is B effective. Okay. So what is B effective? B effective is given by B effective. It was given by B minus D J into J plus 1. Okay, so B effective term was introduced, and this was discussed. Next, the next lecture, the moment of inertia was calculated along different axes for different molecules, and then they are shown that which on what we on the structure of molecule, how this moment of inertia depends, and calculating this moment of inertia, what examples or what information you can give about this molecule. And it was discussed that three types of molecule could be there. Three types of molecule. One should be spherical top, which is for tetrahedral or octahedral molecule, for which Ia is equals to Ic, Ib is equals to Ic. Then there was some concept of spherical top, sorry, symmetric top. So this symmetric top molecule can be divided into two also categories. One could be prolate, other could be oblate. Okay. So for prolate, the condition should be Ia should be, for prolate molecule, the condition should be Ia less than Ib and Ic equals Ic. That means this Ib and Ic are equal, but Ia is less than both Ib and Ic. Or it could be oblate, and for oblate, the expression should be Ia is equals to Ib. These both are equal, but they are less than Ic. Okay. And another thing could be asymmetric top molecule. Sorry. As asymmetric top. For this, the condition should be Ia not is equals to Ib, which is not is equals to Ic. So these three types of molecule were discussed that one should be it could be spherical top, for which Ia is equals to Ic. That is, I is the moment of inertia along different axes, and this if these three are equal, then we can see that this molecule is spherical top. But if Ia is less than Ib and Ic, where Ib and Ic both are equal, we can see that this is nothing but prolate symmetric top molecule. Prolate symmetric top. And if Ia and Ib both are equal, but this is less than Ic, then we can say that this is oblate symmetric top molecule. And other thing could be possible that Ia is not equals to Ib, which is not equals to Ic. For this case, this is known as asymmetric top molecule. The normal water molecule comes under this category, this asymmetric top molecule. Water, hydrogen peroxide, this kind of molecule comes in this category. Okay. And then there was a discussion on this OCS molecule. For this was calculated that what should be the moment of inertia for OCS molecule. It was very much clearly discussed by Professor Sayan Bakshi. And then in the lecture 20, it was discussed about water molecule. Why water is called asymmetric top molecule? Because they have shown that in case of water, when you have calculated this Ia, Ib, and Ic, and they have seen that, and with taking the bond angles and bond length values known, they have seen that these values are Ia is not equals to Ib and not equals to Ic. For water, it was shown that Ia not equals to Ib, not equals to Ic. So they have said that since this condition is satisfied by asymmetric top molecule, so water is a asymmetric top molecule. Next, in next lecture, there was a discussion on quantum mechanics. Some quantum mechanics were there. That's the transition moment. What should be the transition moment integral for rotational transition? It was discussed here. Okay, how to write it, and for then it was discussed. It was written and in polar coordinate. That in terms of psi r, and in psi r, it was shown that psi r is a function of this capital theta, function of Lm and theta, and phi, which is a capital phi, with a function of only m and in a function of phi, small phi. Okay, it was shown that, and from this this how to write this theta lm, there was some new concept which was discussed. There was certain form which was discussed, which is called Legendre polynomial. Okay, how to write this theta term, and from for different n and different l and different m value, how it is changing, it was discussed clearly in the concept of Legendre polynomial. And then from that, Professor Anirban Hazra has done the integration of psi mu psi, because it was already discussed that to see if a transition is happening in the system or not, you need to find that its transition moment integral is non-zero. So that's why transition moment integral was calculated, and it was shown that to be non-zero, the condition to be this transition moment integral non-zero, it must satisfy the condition that delta j should be is equals to plus minus 1, and thus it becomes the selection rule for rotational transition. So in this week, I will discuss some questions regarding these regarding the topics that was discussed in these 5 lectures, and then I will give you some new ideas about this. So let's start. So this is the first question, that the lifting of degeneracy in presence of externally applied electric field is known as, this the Stark effect, Bohr effect, Zeeman effect, or mutual exclusion principle. So what should be the
Stark
answer?
effect.
Stark effect. Okay. So do you know what is Zeeman effect?
No, sir.
Okay. So yes, you are correct. Uh, you can find this reference in lecture number 17. That was what is Stark effect and why I am saying this is a Stark effect. So first, let me go to this diagram. You can see here in the left I have written energy, and here, yeah. So this is written energy. This is going up, and this is the J is equals to 3 level. Okay, J equals to 3 level. And here I have written also that there is no field, no electric or no something, no perturbation is there. So you see any other lines here? No, you cannot see, because this is already all degenerate. In J is equals to 3, you can see when you are not applying any kind of field, you will see just one line. When you are taking the spectrum, you will see just one line when there is no field. But as soon as you are applying some field, you can see that this degeneracy is broken or degeneracy is uplifted. Okay, how it is uplifted? This is uplifted in these 7 states. So why this is 7 states? Because I've discussed already that J is equals to 3 state, and so what should be the degeneracy for J equals to 3? Oh, sorry, I made a mistake. Sorry, it was my mistake. It is not J equal to 3 state, it is J equal to 6 state. Sorry, apology for this mistake. And this would be J equals to 6 state. So what should be the degeneracy for J equals to 6 state? For J equal to 6 state, degeneracy will be 2J plus 1. You know this? 2J plus 1. For
Yes.
J equal to 6, it will be given as 2 into 6 plus 1. So how many states? 13 states. Okay. So how will be they named? They will be plus 6. Sorry. They will be minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 5, 6. So you can count here that I have written 13 states: minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6. Total 13 steps are there. But when this degeneracy is broken, the important thing that comes in mind that what should be the value of mod mg. This was also discussed that what should be the value of mod mg. That means mod mj means for minus 6 and for plus 6, the value will be 6. For minus 5 or plus 5, this will be 5. Okay. So these two states, that is minus 6 plus 6, minus 5 plus 5, minus 4 plus 4, these states would be of equal energy. And that's why you can see in presence of field how they are broken here, that, yeah, here plus 6 minus 6 will be there, plus minus 5 will be there, plus minus 4 of same intensity, sorry, same energy, plus minus 3, plus minus 2, plus minus 1, and 0. Okay. So what was your degeneracy for j equals to 6? It is completely broken for the j equal to 6 states. And this field presence of field, the field could be of two types. Fine. This external field, this external field could be of two types, right? Either, okay, I'm writing. So this external field could be of two types. Okay. Either it could be electric field, or it could be magnetic field. Okay. So when you are applying some, I am writing in presence of some field, that what kind of field would be this kind, the two kinds of, generally these two kinds of fields will be there. It could be either, it could be electric field, or it could be magnetic field. In both the cases, whether it is electric field or it is a magnetic field, you will see the splitting of these levels, and the degeneracy is broken in both the cases. Okay. So if this degeneracy of this rotational level, suppose in this case it is broken by electric field, this is known as Stark effect. Okay. So if this electric field just splitted these energy levels, that is the degeneracy is broken in presence of this electric field, it will be known as Stark effect. And if it is broken in presence of magnetic field, some static magnetic field is there, then this is called Zeeman effect.
Zeeman.
Now you got it?
Yes.
Okay. The same thing, just the fields are different. If it is broken by electric field, it is called Stark effect. If it is broken by magnetic field, it is called Zeeman effect. So in this case, you can see that the applied field is electric field. Applied electric field. Okay, externally applied electric field. So it could not be Zeeman effect. So it will be only Stark effect. Okay. So do you know about, do you know Bohr effect? What is Bohr effect? We have learned it from the basic chemistry. And do you know about mutual exclusion principle? Do you know about this
Yes,
mutual
sir.
exclusion?
Poly
What,
mutual,
what
poly
is this?
mutual exclusion.
Hmm.
Poly mutual exclusion principle.
What does it say?
Mm.
Where are you? Have you heard this?
Two or more identical particles with half integer spins cannot occupy the same quantum state.
Yeah, yeah, yeah. And another also there is another rule for mutual exclusion principle, that is you will learn in this vibrational spectroscopy that for the centrosymmetric molecule, whenever there will be different vibrational mode, the vibrational mode which will be IR active, they will be Raman inactive, and for that will be Raman active, that will be IR inactive. So this is also a mutual exclusion principle. Okay, that we will learn in the vibrational spectroscopy. So you have learned about all these things, and you know that this answer will be Stark effect. Okay.
Yes, sir.
Okay. So this is the second question. Which of the following molecules are not spherical rotors? So this is SF6, SiO2, CCl4 and CHBr3. Which of the following is are not spherical rotor? Right? Know what I said? I'm giving you a little hint, then you will be able to understand that. I have said that for a molecule to be a spherical rotor, you first need to know what should be the condition. Spherical rotors, the condition is IA is equals to IB is equals to IC. Right? I have said that IA is equals to IB
Yes,
is
sir.
equals to IC. And this is generally occur for octahedral and tetrahedral, octahedral and tetrahedral molecules. Okay, this generally happens for octahedral and tetrahedral molecules. So to answer this question, you would just need to find which one is octahedral and tetrahedral. Is there anything octahedral or tetrahedral?
SF6,
SF6, what is the structure? Octahedral or tetrahedral?
octahedral,
Octahedral, right? SF6, I'm writing it. SF6,
then CCl.
huh?
It would be tetrahedral,
Which one?
carbon tetrachloride. Third one.
Third one. CCl4 should be tetrahedral. Any more? The other two? Okay, I'm just drawing it. Yes. So have I written it correctly? SF6.
Yes,
So it is octahedral, right? And what I have said, this SF6, since it is an octahedral molecule, so it will be to its this moment of inertia at different directions will be equal. So it will be spherical rotor. So it will be spherical rotor. Next, okay, I am going with your example CCl4. So is this the right structure for CCl4?
yes, sir.
Yes. So it is a perfect tetrahedral. It is a perfect octahedral, and this is a perfect tetrahedral. So for this kind of molecule, your IB, IB, IC will be equal. Okay, because in all side you can see this only F is there, only Cl is there, so your mass will be equal in all directions. So these two molecules will show spherical rotor, will be spherical rotor. Now I am coming to the next molecule. Which is the next molecule? Suppose I am taking silica, SiO2. So I am not going to the practical side, but that SiO2 is not exist as I will show you in theoretically, because it exists as a linear chain or a polymeric chain. It will exist, but for the basic understanding, what should be the structure of SiO2? You could tell me.
It will also वो भी tetrahedral होगा.
SiO2 tetrahedral होगा. अच्छा. Okay. So I am giving you some hint so that you can understand. So you know the structure of CO2, right?
Yes.
So what will be the structure of CO2?
C attached to two oxygen molecules.
What should be the structure? How they are attached? Is they linear or they are bent like water? Or what?
Bent.
CO2 is bent. No, CO2 is not bent. CO2 is a linear molecule. Okay.
Linear.
CO2 is a linear molecule. Just like here is a carbon. You can see my hand. There is carbon. This is one oxygen, and my right hand is another oxygen. So they are like that. CO2. Okay. Now you know that carbon. See, if you go through the periodic table, you can see that this carbon and they are in the next step there is silicon. Okay. So if you just replace this carbon with the silicon, so it will give you the structure of silica, SiO2. Okay, this is the structure
Yes.
of SiO2. General structure from theoretical calculation. Now I'm not going to the practical side. Okay, so this silica will have linear structure, linear. So I said that for linear molecules, this is different scenario because your moment of inertia at one particular axis will be zero. For linear molecule, it is shown that Ia is equals to 0 and Ib is equals to Ic. Okay. So it will not satisfy the criteria for a spherical rotor. So this will not be a spherical rotor. SiO2 will not be a spherical rotor. Now I am coming to CHBr3, the last one. CHBr3. Okay. So what should be the structure?
C in the middle,
Hmm.
H to the left side, two
Left.
Br molecules to the right side, and one Br molecule hanging up.
You are saying like this.
Yes.
So what kind of structure is this? Suppose I have some bond here. Okay. Suppose I have some Z kind of thing. Then it will form a structure. You know what this is? What this geometry is?
Trigonal,
Trigonal,
pyramidal.
trigonal bipyramid or trigonal bipyramid geometry. Okay. This will be seen when you have only 5 bonds. Okay. But when you have 4 bonds, you know here that you have 4 bonds. So with 4 bonds, 4 bond pairs, and you have no lone pair. You know this VSE pair theory? You've learned this, right? VSE pair, valence shell electron pair repulsion theory.
Yes.
Yes. So just a recap that you can see here there should be 4 bond pair, no lone pair. So it could have two geometries possible. Either it could be square planar or it could be tetrahedral. Okay, just like your CCl4. The structure will be just like your CCl4 structure. Okay. So its structure will be tetrahedral, but here some restriction is there. So first understand that why it is tetrahedral, because it has four bond pairs and there is no lone pair. So this four bond pair should corresponds to either a square planar structure or it could be tetrahedral structure. Fine. So here it should be show square planar structure is observed in some cases, but in such cases, in these cases, you will observe this this structure. This is tetrahedral structure. So now, what is the difference between these two, or are these two structures apparently same? Are these
except
two
for
formed?
the
Uh,
hydrogen molecule.
except for the hydrogen. Exactly. Here, one hydrogen is there and three bromines are there. So your mass, the distribution of mass is not the proper side. Okay, it is not properly distributed. So it will, for this case, you can see for this case, it will not be IA and IB and IC. These three will be not equal. You will see, but and if you have followed the lecture, you can see that for these cases, it is possible that this will show you the structure like IA is equals to IB, which should be less than IC. Okay, so your moment of inertia calculation, if you do this, because what is happening, what is the difference between CCl4 and CH3? That there are four chlorine atoms attached with this carbon in case of CCl4, but when you are dealing with CHBr3, it is showing that three bromine atoms are there and one hydrogen is there. So the mass is not evenly distributed. Bromine's mass is much higher than hydrogen. So it is not evenly distributed. So if you go to and measure this moment of inertia for this molecule, you can see that in this case it is observed that Ij is equals to Ib, which is less than Ic. So it will not go under this category of spherical rotor. It will not show the category of spherical rotor. But I have also mentioned when this condition is arises. When this condition is arises, or what should be the molecule if this condition shows that two axes are equal, which is less than another axis. Okay, I'm just going back. You will understand. Yeah, you can see here what I've said. Yeah, you can say that if Ia less than Ib, which is equals Ic, this will be called prolate molecule, prolate symmetric term molecule. And if Ia is equals to Ib, which is less than Ic, which is called oblate molecule, oblate symmetric term molecule. Now I am coming to this case where you can see here what is the condition. Ia is equals to Ib, which is less than Ic. So what should be the kind of molecule is this?
Oblate.
Oblate, exactly. But not oblate. When you will write oblate symmetric top, because symmetric top is divided into two categories. Either it could be prolate or it could be oblate. So if this condition is satisfied, then it will be called oblate symmetric term molecule. Okay. So in this case, I have discussed as four molecules are there, and you can see that for SF6 and CCl4, these two will show spherical rotor, but the SiO2 and CHBr3 they are not spherical rotors. So can you guess? Who is there just responding? Can you please guess which kind of molecule is SiO2? Just recall it. IB is equals to IC. Okay, that means they have some logical values. Some values are there for IA and IB. Sorry, IB and IC, but IA is 0. So what should be the condition? It will be written as IA is less than
Prolate
IB.
molecule.
Exactly. IB is equals to IC. So it will be prolate symmetric top. Right?
Yes, sir.
Yes. It is the prolate. Okay, prolate symmetric top molecule. So now coming to the question. The question is said that which of the following molecules are not spherical rotor? So I have to find something which is not a spherical rotor. SF6 is a spherical rotor. SiO2 is not a spherical rotor. It is a prolate symmetric molecule. CCl4 is a spherical rotor. And CHBr3 is a oblate symmetric molecule. So our answer will be in this case, it will be SiO2 and CHBr3. We understand that?
Yes, sir.
Okay, fine. So this is a straightforward question. You should answer this. Degeneracy can be written given by which expression? J plus 1, 2j plus 1, 2j minus 1, j square.
2J plus 1.
Yeah, I have discussed it on the previous day that degeneracy is given by this expression 2j plus 1. But for some people who will see this lecture in later, for them just I want to say that for the rotational quantum number j, for rotational quantum number j, number of allowed mg values is the degeneracy. So number of allowed values of mj is the degeneracy. Okay. So for any rotational level with quantum number j, the mj values could start from minus j, they will go down, then will be 0, then they will go to plus j. So from 0 minus j to 0, there will be j values. From 0 to j plus j, there will be another j values. So how many values are there? 2j. And you can see this small thing is there 0. This will be another value. So this will be the degeneracy which will be given by 2j plus 1. So, so your answer should be 2j plus 1. Okay. Okay, so I am moving to the next question. It is saying that Maxwell-Boltzmann distribution between two states I and J, where I is the ground state and J is the excited state, it can be written as these four options are there. So what should be the correct answer? Try it. Which should be the correct answer?
Don't know, sir.
Okay. Okay, I will discuss. So you can find this answer also in lecture number 17 and the straightforward relation that it says suppose you have two states. Okay. Okay. suppose we have two states. Okay. Suppose this is I state I. What is mentioned here? That this is state J. Okay. Suppose number of molecule here is Ni. Number of molecule here is Nj. Fine. So for I state there are Ni number of molecules, and for J state there will be Nj number of molecules. Suppose now you are having a transition is something happening. Okay. Or what should be the distribution? What should be the value of Nj? So your Nj, Boltzmann said that Nj and Ni will follow this relation, C to the power minus Ej minus Ei by kBt. Now, if you ask me that from where this relation comes, I will suggest you, if you have read this statistical thermodynamics or statistical mechanics, you will understand that. Or if you are don't read, you will later learn. For now sake, I'm just going to tell you that this term, this e to the power minus Ej minus Ei by kBt, this term actually arises that this actually it was said that the probability of a state it's proportional to this term. Okay. Now, if you know that the probability of a transition, this depends upon the population. So, relating this probability with population, this relation was derived. That Nj by Ni it is e to the power minus Ej minus Ei by kBt. But it was seen that some states are suppose degenerate states. Okay. Suppose in your I state, what you have seen just only one I, there should be 3, 5, 7 I states. Okay. So to introduce this degeneracy also, it was introduced that the dj by gi term. So if nj is on the upper side, gj will be on the upper side. If nj is the lower side, gi will be the lower side. So to the power minus ej minus ei by kBt. Now you have seen previously when we have discussed that the energy difference between two states, when we have talked about this term, this energy difference, we have seen that it was expressed in terms of delta E. Delta E is defined as energy of the excited state minus energy of the ground state. Okay, this is called ground state and this is called excited state. Okay, so delta E is defined as the energy difference between this excited state and this ground state. So now I can easily replace this. This will give me Gj by Gi into exponential minus delta E by kBt. So this is the expression. This is the Boltzmann-Maxwell distribution. What you have seen that Ni Nj by Ni defined as e to the power Gi by Gj by Gi e to the power minus delta E by kBt. Fine. Now I am coming to the previous one. Okay. So you can see here that your energy Nj by here. So what should be the distribution? This is
Second.
the Nj by Ni. What I have said that it will follow Gj by Gi into e to the power minus suppose delta E by kBt. Okay. So this is the Maxwell-Boltzmann distribution. Nj by Ni is equals to Gj by Gi e to the power minus kBt. Okay. This will be plus, sorry. So this is the Maxwell-Boltzmann distribution. That's Nj by Ni should be equals to Gj by Gi into e to the power minus delta E by kBt. Now in this case, We have seen that the options are given that your I state will be in the top and J state will be in the lower side. Okay, numerator and denominator. Okay,
Fourth option.
so sorry,
Fourth option will be the answer.
fourth option. Yeah. So your what should be your Ni by Nj? This will get just get reversed. Okay, so it will be your Gi by Gj e to the power delta E divided by kBt. Because when you are just reversing it, your Ni by Nj by Ni will become in Ni by Nj, Gj by Gi will become Gi by Gj, and since your exponential term power of the exponential was negative, when you are reversing it, it will become positive. So you have to find which option is there. Now I'm going by one. Ni by Nj, Gj by Gi. It will not be possible. So this is will not possible. Next one, Ni by Nj is equals to Gi by Gj into e to the power minus delta E. So this is also not possible. Nj by Ni is equals to Gi by Gj. Not possible. Nj by I is equals to Gi by J. This is not possible. Ni by Nj is equals to Gi by Gj into e to the power delta E by kBt. This is the correct answer. So the correct answer I will also correct it in the slide. It will be a positive sign. Okay. So you will understand that.
Yes, sir.
Okay. So this is the fifth question, which states what should be the spacing between two pure rotational spectral lines. What should be the spacing between two pure rotational spectral lines? It was shown that in rotational spectrum, just get these kind of lines. Ignore my drawing, just understand the concept. Okay. Uh, so first of all, you need to know that in case of pure rotational spectrum, are the rotational spectral lines are separated equally among themselves or not? First, you need to know that. If this is the thing, just you need to find the value. They will give you the answer. So for this, you just tell me that for pure rotational spectrum, are the lines separated equally or they are equally spaced or not?
They are equally spaced.
They are equally spaced, exactly. So what should be, what is the spacing? If you can see, I mean the previous day I have shown that first line comes at 2b. Okay. Next line comes at 4b. Then next one is 6b. Then next one is 8b. So you have seen that spacing is equal, that is 2b. So the spacing, what is the spacing value?
2B will come.
2b will come, exactly. But remember one thing, guys, this will be only possible for pure rotational line. When you have something non-rigid rotor thing, the rotational lines will not be equally spaced. Okay, so for pure rotational line, these equally spaced lines will be there, and so they will be separated by factor of 2b. Now got it? Okay.
Yes.
Yeah. It's just very straightforward question I have discussed so far. So, what should be the correct moment of inertia for prolate rotor? Prolate
IA
symmetrical rotor.
greater.
Which one?
IB is equals to IC
IB is equals to IC. This one?
greater than IA.
Huh? Huh? This one? Which
Yes.
one? Third one.
Third one.
Okay, fine. Okay, just the concept of that you can find this reference in also lecture number 19. That suppose molecule spherical top molecule. Small concept I will discuss here. Spherical top. Okay, so it could be divided into two types. One should be prolate, another should be oblate. Fine. So for the case of prolate molecule, yeah, for the case of prolate molecule, the relation is IA less than polarity is IA less than IB is equals to IC. Here we have given it correctly. Problem molecule, the relation is IA equals IB, which is equals IC. Okay. So for the sake of this question, you've already got this answer. This for polar molecule, this is the condition. This is the condition. For polar molecule, IA would be less than IB is equals to IC. You have guessed it correctly. Now, suppose I am taking a prolate molecule. Okay. Some example. Suppose methyl. Oh, okay. From the previous one, I have taken the example of CHBr3. Do you know what is the name of this compound?
Bromoform.
Bromoform, exactly. Just like chloroform, this is bromoform. Okay. And then the other side, I am taking for oblate for the example of oblate molecule. I am taking another thing. Oh, sorry, I have taken that. This would be the opposite one. Okay. So suppose I am taking example of solid molecule so that you can understand that I am taking suppose methyl chloride. And for the case of open molecule, I have shown the example of CHBr3 bromoform. Okay, so for simple case, I am replacing all with bromine. Sorry, chlorine. So that will be easier to understand. Okay. So for spherical top molecules, I am dividing it into two categories. One is prolate molecule, another is oblate molecule. Okay. So from for this prolate, the condition is IA will be less than equals to less than IB, which is equals to IC. So one axis. That means if you have moment of inertia along three axes, just remember that if you have moment of inertia about three axes, the moment of inertia about one axis will be less than the other two, which are equal. But if the moment of inertia of the other axis is higher than this is equal to moment of inertia, then it will be oblate molecule. Okay. Now just just focus on this thing. So you know which one is much higher in mass, or which one is heavier. This chlorine is heavier or hydrogen is heavier?
Chlorine is heavier.
Chlorine is heavier. Okay. So the most of the mass will be confined under this region. Okay. The center of mass will be like this in this case, and this most of the mass will be covered toward this chlorine. So you will see these molecules. If you calculate it, it will look like this one. Okay, just a rod like thing, because your most of the mass will be in the chlorine side. So it will be also called rod like molecule. And you can see here, for these rod like molecules, porolate molecules, you can see these rod like molecule are also observed for linear case also, right? Linear case, they are not, they are on the same plane, they are just only on the straight line. Okay, they are also look like slot. That's why when I was discussing about this SiO2 molecule, I have said that this is a linear molecule, and I have shown that this Ia will be less than Ib, which is equals Ic, and which will be a prolate symmetric molecule. So you can see from here also that your any linear molecule will be prolate symmetric molecule. Okay, so this is rod like molecules. Now I am coming to oblate. For oblate case, the condition is that Ia will be equals to Ib, but it will be less than Ic. How? Suppose the same thing I am repeating here, that here you can see three chlorine atoms are there. So that is, and you have, since you have said that chlorines are much heavier than hydrogen, so more mass will be confined in this site. So you will see these molecules like this one. Okay, this will show disc-like structure. Okay, so what have you understand from this question? That for any symmetric term molecule, whether it is prolate or oblate, it will show some kind of structure. If it is prolate, it will show rod-like structure, which is also possible for linear molecules. But if it is a oblate molecule, it will show disc-like structure. Okay, this is the answer. I have written here that the condition for a molecule will be prolate symmetric top is, this is the condition, Ia will be equals to Ib, Ia less than, sorry, Ia less than Ib, which is equals to Ic. And they also, these molecules are also rod line molecules. Rod line molecules. What are examples? Examples are the CH3CN, CH3Cl. If you go for CH3CN, you can also see that your CN is much heavier, you know, than hydrogen. So the mass will be confined almost there, and also so it will show this rod light of structure. So you understand that?
Yes.
Okay. Now this is also a straightforward question. What should the answer?
Symmetric top.
Symmetric top. Which one? Which symmetric top? Prolate inlet, a prolate oblate?
Oblate.
Oblate, okay. You have said oblate because of this disc-like structure.
Yes.
Uh, yeah. Okay, so I am discussing that. Suppose this is a water molecule. So your mass, center of mass will be like here. I'm just drawing the axis. Suppose this is z axis, this is y, this is x. I'm drawing very badly. Okay, let me use another color, so it will be very beneficial for you then. Suppose my center of mass is here. Okay, so this is my x, this is my y, and this is my z. Suppose, okay. So if you are going to calculate your moment of inertia along different axes, you can see in case of water molecule. So do you know what is the angle between this bond, these two each bond?
109.
109 is happens for all the tetrahedral molecules. Okay, so you are correct. You are correct because water molecule structure is generally this: oxygen, hydrogen. Correct. This is the correct structure of water. Hmm? This is the structure of water, right?
Yes.
Yes. But what I have mentioned you that for VSEPR, what I have mentioned that in VSEPR theory, it was also mentioned that the lone pair when they repel each other, when their repulsion is there, because you know what is lone pair? There is just electron density. Okay, we have some electron density here, some electron density here, so they will repel, right? So this lone pair repulsion is always better than lone pair and bond pair repulsion, and also which is greater than bond pair repulsion. This is general VSEPR theory, VSEPR theory. So your bond angle initially was 109.5 degree. Okay, this is tetrahedral bond angle. But your water, this lone pair repulsion will push this two hydro OH bond. You can see my hand here. This was your general angle, but your repulsion will be there, will push this towards this one. Okay, so bond angle will get reduced. So it will reduce to how much value? This value will be 104.5 degree. Okay. So initially, you are correct that for just like for tetrahedral molecules, this bond angle will be 109.5. But for what molecule, since this lone pair repulsion is there, the bond angle will reduce to 104.5 degree. Got it? So for water, this case, this OH bond angle is 104.5 degree. Okay, and I have the value for this R. You can find it in Google also. The bond length is 0.958 Armstrong. Okay, and you have also mass of hydrogen, that is 1 mu, the mass of oxygen, which is 16 mu. Okay, so now if you are going to calculate it, you have just need to calculate separately what is Iz, what is Iy, and from that you get Ix would be calculated as Iy plus Iz. So what is Iy Iz? Iy Iz at the moment of inertia on different axes. When you are calculating moment of inertia along z axis, since your oxygen molecule will fall under this category, this z axis, oxygen molecule will, suppose here is your oxygen molecule and your axis is like this. So this oxygen molecule will not considered for moment of inertia calculation. Okay. So up to considering this one, this is all done in this lecture number 20. So if you calculate it, you will find, and if you put the value finally for what are that this theta, r, mh, and mo, will find that what will be your, so you will find that your Ix is not equals Iy. So I don't have the values with me, and I not equals to Iz. Okay. So what you need to do? You just need to do this. This was done by Professor Bakshi. He has shown that if you can calculate this Ix, Iy and Iz along different x and y and z axis, and if you were you can see then that these values are not equal, values are different. So this condition is satisfied by, you need to find which kind of molecules will satisfy this condition. So which kind of molecule satisfy this condition? Hmm?
Asymmetric.
Asymmetric top. Okay. So for water, it is seen that for water, calculating the moment of inertia along different axes, it indicates Ia not equals Ib not equals Ic. So it falls under the category of asymmetric top molecules. So do you want my answer?
Yes, sir.
Okay. So up to this, I have discussed with simple examples that what kind of molecules could be spherical top molecule, which kind of molecules would be symmetric top molecule, and in symmetric top you could have two different kinds of molecule. One could be prolate, one could be oblate. For prolate, what kind of structure should be like? They will show rod-like structure, and for oblate, they will show disc-like structure. Here for this water I have shown that also the an example of an asymmetric top molecule for which all the moment of inertia along different axes are different. So I am moving to the next question. Oh, again the same thing. The next question is, there is one prolate, one oblate. We have to find which is the correct combination. Okay, so I'm just going step by step, and then I will ask you, then you will be able to understand.
Okay. CH3CN is prolate.
CH3CN is prolate, okay, and the CH3CN is attached with one SF6, and another is here is CH6H6. So, so you have if I am going that you are right, then I am going with you are right. Then you need to find that SF6 is, or between SF6 and C6H6, either one is prolate, oblate or not, or both are not oblate.
SF6 is oblate.
SF6 is oblate. I have discussed that SF6. What kind of structure is SF6?
Octahedral.
So for octahedral molecule, is it oblate?
No.
What was that?
It is a spherical top.
Okay, exactly. Another spherical topology. Okay. Okay. So I'm going example by example. So so this was already I have said. Prolate and oblate can be classified in terms of the moment of inertia along different axes. This for prolate, IA less than IEB equals IC, and for oblate, IA equals IB greater than IC. Okay. So sorry. I'm again mistake. This will be less than. Too much mistakes are today. This will be less than. I will correct it in the slide. Okay. So IL equals IB, which is less than IC. And also proton molecule shows rod-like structure, and oblate molecule shows disc-like structure. The same thing. Now I am going molecule by molecule, and then you have to find which one is prolate, which one is oblate. Suppose I am going with CH3Cl. Okay, I'm taking a new slide. The big question. Okay, first molecule was CH3Cl. Right? What will be the structure? C hydrogen will be the, just like CH3Cl, CH3Cl will have the same structure. Okay, this is the structure of CH3Cl. So you can see, just like previous cases, here also the moment of inertia actually directed more towards which side is CN side, because the other side there is lighter hydrogen atom. So it will show again this rod like structure. This rod like structure. So what kind of molecule will be? Will be prolate.
Prolate.
Exactly. This is the first molecule. So what was the second molecule? CO2. CO2. So let me just write all these molecules: C6H6, SF6, C6, H6, SF6. Okay, now for CO2. Well, this side is done. CO2. What is kind of molecule is this? CO2. CO2 is a linear molecule.
Prolate molecule.
Hmm. CO2 is a linear molecule. And also, I have discussed that for linear molecule, they was also so rod-like structure. Okay. For that, IA is equals to 0 and IB will be equals to IC. So it will satisfy this condition that IA is less than so for this case IA less than IB, which is equals IC. So it will fall under again prolate category.
Prolate molecule.
Prolate category. Prolate molecule. So two prolate molecules I have got. Okay. So now for C6H6. What is this? Oh, every chemistry student know benzene, right? Benzene, you can see from the structure of benzene, benzene is disc-like. Okay. So for benzene, if you're going to calculate IA, IB, and IC, you will see the relation like this. So it will be under oblate category. Okay. So for benzene, if you are going to calculate IA, IB, and IC, you can see, you know the structure of benzene. Okay. So if you see, it looks like a disc. Okay. So since benzene looks like a disc, so it will show oblate kind of structure. So it will be oblate symmetric of molecule. Now I am going for SF6. So I have already drawn this structure for SF6. So for SF6, SF6, yes, this is the structure. So it is perfect octahedra. In terms of structure, I am saying this is perfect octahedra. So IA will be equals to IB will be equals to IC, and it will go under spherical top. Exactly, spherical top. So you can see among the four molecules that are given, one is two are prolet, one is oblet, another is spherical top. Now I am going back to the main question. So it was discussed that which pair you have to choose the correct combination. One prolet is there and one oblet is there. Okay, so I am seeing more than one options are correct. So you have to choose that one. Which are correct?
Third option.
Why not the second option?
Yeah, second one also.
Second one also correct. Carbon dioxide, I have shown it is a prolet structure. C6H6 also a prolet structure. So both options are correct. Okay. So another option I will add here that this is the first option. Second one will be CO2 along with C6. Okay. You got this answer?
Yes, sir.
Okay. Now coming to the ninth question. Which of the following relation is not associated with rotational selection rule? That molecules must have a permanent dipole moment. Second option is delta L is equals to plus minus 1. If for this you can consider the delta L as delta J. Delta M is 0 plus minus 1, and also molecules must have an temporary dipole moment. So what should be the answer?
Molecule must have a temporary dipole moment.
Molecule must have a temporary dipole moment. Okay. I have here question is not associated. I've seen that. So need to find out which condition is main necessary for a rotational selection. Then if this is there, then we will ignore that. And then we will find the answer which is not associated with rotational selection rule. So you can find this answer in lecture number 21. So I have said what I have said, that the rotational transition for rotation, I can write here. For a rotational transition, you know, is the criteria is that for any transition, suppose for any spectroscopic transition, the criteria is molecule have non-zero dipole moment, but need that this dipole moment is permanent dipole moment. What is mean by that? Because this is meant by that the dipole moment is not changing with time. It will have a permanent dipole moment. Okay, so this is the very first condition for a rotational transition to happen. That your mu should not be equals to zero. It should be not equals to zero. Why? Why it should be not equal to zero? Because for the and it was also proved using Fermi Golden rule that the transition probability depends upon mu, and the factor is called transition moment integral. I have said that from the past two classes that for a transition to happen, your transition moment integral should be non-zero. And this in this expression of this transition moment integral, what is for the expression? Suppose a transition is happening from state M to state N. Okay, there is just state M and state N. This is state M, this state N. So f function should be psi M and s function here should be psi N. So the condition should be psi N mu. I know you know about bracket notation. So in the bracket, it was discussed there also already that this this value, this is called transition moment integral, this should be non-zero. For transition to happen, these factors should be non-zero. But for your mu, if mu is becomes zero, then this whole factor will be zero. So your transition will not happen. So for this, you need to your mu need to be zero, and for mu need to be zero, this will also not change with time. So it will have you need to have a permanent dipole moment. So what is the first condition that is written here? That molecule must have a and it will be a molecule must have a permanent dipole moment. It is correct. Next, in the next case, you have seen that for the rotational transition, you have the selection rule that was derived as delta J is equals to plus minus 1. Okay, this was the selection rule that was derived also from the view of spectroscopy and also from the view of quantum mechanics. From both sides, it was derived that for a transition to happen, also you need your delta J value should be equals to plus minus 1. So here, our second option, which is stating that your delta L is equals to plus minus 1, it is a condition for rotational transition. Now, in the very beginning, I have said you have condition for rotational transition, but suppose there is when there is no field, it is correct. Delta G is plus minus 1, it is a rotational transition. But when you have a magnetic field, your M the degeneracy will be broken. All the M levels will be separated. Okay. So for this, there will be new selection rule will say that delta J plus minus 1 will be there, but also delta Mj it could have only two values 0 and plus minus 1. Okay, it was also selection rule for when there is the condition for breaking of this degeneracy. There is this is also the selection rule that your Mj will be delta Mj, that is the transition between two Mj levels should be is equals to 0 or plus minus 1. So you can see here that the first three conditions will be satisfied by rotational selection rule. But the fourth condition here, which is written as molecule must have a temporary dipole moment, it is not true because molecule needs to have a permanent dipole moment to be rotationally active. So your answer should be this one, fourth one. Got it?
Yes.
Okay. So coming to the last question for today, which I am going to discuss that what is a rotational eigenfunctions known as? Rotational eigenfunctions are known as which one? The spherical harmonics, Hamiltonian, Jacobian, or transition moment integral. What should be the answer?
Transition moment integrals.
Transition moment integral. Okay, fine. Okay, I'm going to that. Okay, I will just tell you it. So you can find this answer also in the reference in lecture number 21. So can you remember what was the Schrodinger equation for this rotational transition?
No.
No. Okay, I'm writing it. Schrodinger equation. The very fundamental equation in quantum mechanics. If you will you will learn a lot about quantum mechanics, then you will understand why it is important so much. So your this Schrodinger equation says that, oh sorry, this will not be in bracket R. This means the different thing. Okay? This is the Schrodinger equation. So this is the Schrodinger equation for a rotational transition. That L square by 2I of psi r, this is E psi r. Okay. So now you can see which one is the eigenfunction. Eigenfunction.
Hamiltonian.
Differentiate between these three things. Here, how many things are here? There is some operator. Okay, let me clear you. There is some operator. There is some eigenfunction. So what is eigenfunction? Can you remember? Can you remember what is the eigenfunction? No?
The cap one is the operator.
Step one is the operator, right? No, that's not this one. This whole is the operator. Okay. This whole thing is the operator.
Okay.
Okay. This is what is this L? This is momentum, angular momentum. Okay. So this angular momentum, when you are dividing with moment of inertia, it is giving you the energy operator, and in this case, it is just like Hamiltonian or Hamiltonian H operator. Okay. Now you can see that what is the Schrodinger equation. Everybody, if someone is going to ask you where what is Schrodinger equation, you just say this one H psi equals to E psi. This is the Schrodinger equation. Now what is H? This you need to know. Then you can tell. So in this case, you can see here that H psi equals to E psi. So your operator is H. So what is eigenfunction? How can you define an eigenfunction? A function is to be eigenfunction. Suppose I have a function. Very briefly, I am explaining. Fx equals to e to the power x. So is it an eigenfunction of this operator del x?
Yes.
Why? Why are you claiming yes? If it is no, why no? Okay. Just I am explaining that. It's okay, you can forget it. It's normal thing. Okay. Don't be shy. So if suppose I have this function fx equals to e to the power x. Now this is my operator. I am operating it. So fx on e to the power del x of fx It will give you del del x of e to the power x. So what will be the derivative of e to the power x? Hmm?
EX.
This one. This one. Just e to the power x derivative. It is just e to the power x. Suppose I am writing it with 1 into e to the power x. I can write it. I can write it the e to the power x as 1 into e to the power x. Now you can see, now what was your ex? E to the power x, e to the power x was your fx. Now I am writing this even here. Oh, sorry. So your del del x of fx is equals to 1 into e to the power x. I can write it as fx. I can write it. Yes. So when I've written it correctly, then you can see that clearly follow my words. You can see that there is some operator which is operating on a function to give, there is some operator which is operating on a function to give the same function back multiplied by some value, right?
Yes.
There is an operator which is operating on a such a function that it gives the same function back which is multiplied by some value. So in this case, this is called eigenfunction. Okay. And the value you obtain here, one, this is called eigenvalue.
Value.
Exactly, eigenvalue. Okay. Now can you match these two, this left hand side and right hand side?
Yes.
Yes.
The capital is the whole thing, the operator.
Yes.
Then I R is the eigenfunction.
Psi r is the eigenfunction and
E
what is the
is
eigenvalue?
E.
E is the eigenvalue. Exactly. So you understand that. Good. So my point is mainly that now I'm going to the question. You can see it is written that what rotational eigenfunctions are known as. So you need to know what is psi r. So you need to know what is psi r. So psi r is actually function of theta and phi. Okay. So in the lectures you will see that the psi r, uh, when there is a conversion of this Cartesian coordinate to polar coordinate, that is in your coordinate this was xyz, it will be converted to r theta phi, and you will see that the psi r, it will be function of theta and phi. Also I can write it as psi lm theta and phi. Okay. Now I have this courage to write it as, this is a capital theta. Okay, remember it. So, so capital theta, sorry, it's just, this is capital theta, just like your small theta. This is will be a function of small theta, and there will be some term which is the function of phi, and I will rewrite as phi of phi. Okay, this term, this theta term, will depend on L and M value. This phi term will depend on only M and L value, M value. and it will have a expression. You will can see if you have seen it. I don't know. You will see the lecture. It will have an expression of 1 by root over 2 pi e to the power I m phi. Okay. So how what I've done? This this eigenfunction, I have written it will be a function of theta and phi. So I can separate this theta and part and separate this phi part. Okay. Now phi part is a function of this quantum number m. Part theta part is a function of these two quantum numbers L and M. And also this can be expanded in terms of this theta part can be expanded by this way will be n of Lm into p L m cos theta. So this derivation is out of this context now. So this is a very rough derivation. So from this is a functional form of theta. Okay, this is a functional form of theta. Theta can be defined as this one. So what is the significance? Suppose I need to know what is the value of theta for my level where L equals to 1, M equals to 0. So you just put this value of P here. You just need to calculate this normalization constant. This NNML is a normalization constant. Okay. Constant. Okay. And this part PL of M cos theta, this is a polynomial function. This has another form. So this has the form of cos theta. For this, you just need to put this L and M value, and that will change like it will change. So this is also known as Legendre polynomial. The initial slides I was discussing about that. What is Legendre polynomial? This is the Legendre polynomial. So for different L and M values, these values are different. So you just need to put those values and you will find phi. You know what is phi, sorry, you will get the value of theta. Know what is phi, just multiply it, you will get the psi. And now in this case, since to calculate the psi, you need polar coordinates. So this is also known as spherical harmonics. Okay. So what rotational wave functions are known as? They are known as
Spherical harmonics.
spherical harmonics. Okay. So Hamiltonian, the second option was there. It is not an eigenfunction, right? It is just a operator. So it is not. It would not be a function, right? The third one I'm coming later, but the fourth one it is the transition moment integral. So this is also not a function. You will get this value of transition moment integral in the previous slide. I have mentioned that it will be psi mu psi. It will give you it will give you a number or something else which is not a function. Okay. So it will also not be a function, transition moment integral, and also it's not related to the rotational eigenfunction. The only thing you could uh, debate on this between the spherical harmonics and this Jacobian function. The Jacobian function is known as Jacobian matrix is there, which is the matrix of partial derivatives. Okay, suppose del x, del y, del z. Suppose you have taken this in the matrix form, this will show Jacobian matrix form. Okay, so this is not here relevant here. So your answer here is spherical harmonics. Okay.
Yes.
So do you have any questions up to this?
No.
No. Okay. Fine. So I'm going to post this. Yeah. Okay. So this is done for I. So I am stopping the recording.